right. Okay, let's get started. We got a bit to cover and a little to catch up on, so let's get into it. So first, a quick announcement. Review sessions are starting this week. We had a quick one last week on Tuesday. This week we're going to fully start all 3 review sessions. I didn't really announce these yet. It was just TBD on the course website. But times and locations here, Monday, Tuesday, and Friday, 4 to 6 p.m. at the locations shown here. So check the course website for those. And if you want more review or you just want to stop by, hang out with the TAs, you just want to chat, whatever. They'll be hosting review sessions. The TAs will be giving, review. I don't know what else to say about that. If you want more review, go check them out. If you can't make it till like halfway through, feel free to stop by for just the second hour or whatever. And go get some extra review. Office hours are posted. The schedule is still a little bit in flux as TAs are figuring out their own schedules. But the office hour schedule, I'll update periodically as their hours change. But check them out. All these office hours are outside of Davis 302. Go to the 3rd floor of Davis, the top of the stairs. If you're facing the elevators, turn to the left and go down to the end of that hall. They'll be in that common area out there. I'm working on getting a photo roster of all the TAs so you know what they look like, so you can look for their faces and then say, hey, you're the 115 TA. Until then, just say, hey, I need a 115 TA or anything you got to do to get their attention. Or if you just stand there and look lost, any one of my TAs should approach you and say, hey, I bet you're for 116. Sorry, I said 115. But hey, it looks like you're here for office hours. And then my office hours are in my office, Davis 344. If you want to, if you have something that you need to talk to me, Tuesdays 1 to 3. All right, we didn't quite get to data structures last time, so let's talk about this quickly. I won't go too far into data structures. Most of it's just syntax. I'll try to highlight the differences. And just like types, I'll go a little bit deeper into a few of these data structures. First, there are a wide variety of data structures in Scala. We'll only touch on a couple of these. I'm not going to go in depth into this whole tree, this whole structure of all these data structures, but suffice to say there are a lot. There are a lot in Java as well, and I don't know. There are just a lot of data structures. This is a class, an inheritance tree. We'll talk about this as we get to object-oriented programming, but I want to give just some quick foreshadowing of that. The 3 we'll talk about today, array, list, and map. The array and list are both sequential data structures. They're what you're used to using in JavaScript and Python, using lists and arrays. The names get a little fuzzy sometimes, but there is a fundamental difference between an array and a list, though I believe, I should have looked this one up before lecture, but I believe a Python list is based on an array. Maybe somebody can correct me on that. Maybe it's not. But sometimes the words are used somewhat interchangeably. For example, Java has a class called an array list. Is it an array? Is it a list? Well, let's decide. That one is actually an array, but it inherits the list interface, if you're wondering. And then map is our key value store. So an array, this is a sequential chunk of memory that stores multiple values. So an array, this is where we have indices, where we say, array, give me the value at index 0, index 1, etc. It has to be one continuous block of memory, which will be very important moving forward as we look at memory next week. It's one continuous block of memory. It's one chunk of memory, and then we can access any element of the array by starting at the first memory address and then adding the element number times the element size to be able to access any element that we want at any time. So we have, a mathematical formula where we can get the memory address for any element in the array and access it directly. This does imply that the array is fixed size. If we have one continuous chunk of memory on a RAM stick, well, that next piece of memory might be used by another program or another variable, so we can't just increase the size of this thing without moving it to another piece of memory, which is very expensive. So these are fixed size, sequential, random access data structures. To use them, Just a quick overview of the syntax for an array. If there are more methods you want to use, more stuff, this is where you would be expected to be able to read through the documentation, find those methods, and be able to work with the array however you want. But very briefly, to create an array, change the value of a single array, access a value from an array, iterate over an array. Iteration is going to look similar for all these data structures. And if you want to iterate over the indices, for whatever reason you need the indice, if you want to return the indice of a specific value that you're looking for, you can do that using the to method or array.indices. And the one new thing that I want to focus on, this right here, this type, this is what we call a type parameter. Since Scala is strongly typed, its data structures are also strongly typed in the sense that whenever you create a data structure, you have to specify what type that data structure can store. So in Python and JavaScript, we could get away with mixing our types inside our data structures. We create a Python list. We throw integers in there. We throw floats in there. We throw strings in there. We throw other objects in there. And Python's like, whatever, I got you. I can do this. Scala will not let us do that. It has to have a specific type in its data structures. So this array, when we create an array, we have to specify a specific type that it's going to store, in this case int, and this array can only store values of type int. For its entire lifetime, this array can only store ints, and this variable can only store arrays of ints. It can only store arrays of type int. So our types, our data structure types themselves have type parameters. We have to specify the type that the data structure is going to store. Yeah, question?
Is there a way to determine the length of the array, but you don't know what values you're going to store? You want to determine how big your array is, but you don't know what values you're going to store.
Yes, I don't know the exact syntax off the top of my head, but the question is, can you specify the size of an array when you create it without giving it the values that you're going to store right away? So I want an array that I know it's going to store 100 elements, but I don't know what those elements are yet. There is a way, I just don't know the syntax off the top of my head. But you do have to specify the length of an array. For example, this array is always going to be size 3, and that cannot change. It's fixed size. That array, that chunk of memory that is big enough to store 3 ints is allocated when we create this array, and that chunk of memory can't change its size. We can't just say, hey, I need a fourth, I need room to store a 4th int here. Can't do it. Not allowed. Lists, on the other hand, can change size. So if we want to add new elements to a data structure, a sequential data structure, list is going to be the one we want to use. And list is the one I'll use most often throughout the course, throughout my examples, because we'll have lectures and we'll talk in depth about the linked list data structure, which this list is based on, Scala's list is based on. So I want to just get used to using lists so we can talk about what we've been using all semester when we get to those data structure lectures later on. So lists, unlike array, which is one continuous block of memory, a list is split across our memory in no specified order. So every element in a list can be in a completely different spot on our RAM sticks. They can be all over the place in memory. And each element has a pointer, has a reference to the next memory address of the next element in that list. So to access a list, we start at the first element. Say we want the 4th element of list, we'll start at the first element. Say, hey, first element, where's the memory address of the second element? Hop over to that spot in memory. Say, hey, what's the memory address of the next element? Hop over to that memory address. Ask that element, hey, what's the memory address of the next element? And then hop over to that 4th memory address and then access that element. So we no longer have our random access. We can't just jump right to the 4th element or whatever element we want. We actually have to traverse the entire list to be able to access that element. So this can be more costly for certain applications. If you want to ask a list, hey, what's your middle element, for example, it's actually a pretty expensive operation because you have to hop around memory quite a bit. Whereas array, you could just jump right to it. But this gives us the ability to have variable size. If we want to add a new element to this list, we just go get a new chunk of memory, And then the last element in the list, we just say, hey, the next element, instead of being nothing, is now this memory that I just got over here. So we can expand the size of a list. So some syntax for a list. List creation looks very similar to an array. If we want the first element, .head. If we want to pretend a list has random access and give me the value at this index, we can do that with the apply method. But this does traverse the list. This is an expensive operation to traverse the list using apply. But we can kind of simulate that. Appending an element to the end or beginning of a list, iteration first is the same structure, but appending, I want to talk about this a little bit. If we want to append, either prepend the second example or append the first example to the end or beginning of a list, we have to reassign the list to the variable that was storing it. So these operators don't actually modify the list itself. A list, the values of a list in Scala cannot change. A list, an entire list, is what we call immutable. It cannot change. I created this list with 2, 3, 4. That list forever will always store the values 2, 3, 4. It cannot change. That list cannot change. This variable of type list of int stores this list, and when I append 50 to the end of this list, I'm not modifying this list that I created. I'm actually creating a brand new list with the values 2, 3, 4, and 50 in it. And then I have to reassign that brand new list that I just created. I have to reassign that to my variable. So this variable list, after this assignment, is no longer referring to this list. It's referring to the brand new list that was created when we executed this operation, this append operation. Called this append method. So we'll get into more detail, the implications of that, and we'll dive into all kinds of detail later in the semester. For now, just remember that you have to reassign the list. If you just call this expression without reassigning it, you're going to be wondering where your 50 is, because it's not going to be in your list, because this created a new list. You didn't assign that new list to anything. You just left it on the floor and walked away from it after it was created. And list, your variable, is still going to be referring to this list with only 3 elements. So always reassign your lists when you're trying to modify them, because the list can't actually be modified. We're creating a new list and then reassigning that new list to the variable that we're using. So just be cautious with that. I'll still get that question in office hours. It's fine. It takes a little bit to just remember how to work with these lists, but you do have to reassign them whenever you want to simulate modification to the list. Maps are key value stores. By default, this is a 250 topic, but by default, these are implemented on top of hash maps in Scala. We don't have to worry about quite what that means, but we get the key value store functionality out of these. Variable size and variable values, we can change a lot here. It's not technically true. This is, in Scala, we'll use immutable maps. There's a mutable version, but the hash map itself is variable size and variable values. So map, we have a little bit different syntax. When we create these key value pairs, the big notation here is the arrow pointing to the right. This is read as 2 maps to 4, 3 maps to 9, 4 maps to 16. These are my keys, 2, 3, and 4, and then my values are this 4, 9, and 16. So this is how I get the key value mapping. And a map takes 2 type parameters. The keys and the values can be different types. Now whatever the first type I give this, every key has to have that type. Whatever type I give it here, every value has to have that type. But those 2 types can be different. I can map strings to ints, or strings to doubles, or ints to doubles. I can have all those different combinations of mappings. When I want to add a key value pair, it's the plus operator, and the same syntax we used when we initialized our key value pairs when we created the map. And we are using an immutable map, so we do have to reassign. We created a new map here. We do have to reassign this back to our original variable if we want that change to be reflected in our program. If we want to access a value by key, we can use the parentheses, just parentheses, nice little shorthand, kind of like using an array. And if we want some default value, we can use this get or else, or we can use just get instead of just the parentheses. A few options we have here. The get or else is helpful because if you ask a map for the value at a key, and that key is not in the map, your program crashes. Nothing happens after that. Program just crashes and you can't do anything else. If you use get or else, you have a little bit of fail safety here. If 100 isn't in the map, which it's not, I'm going to return -1 here, and my program does not crash. And then my next line can be like, if y equals -1, do whatever error processing I want to do after that. Iterating over a map, you do still have .values, .keys, like you had in Python, but Scala gives us this nice shorthand, very convenient. You just, in parentheses, name 2 variables, and you can iterate over the keys and values at the same time in a map. So why do anything else, is my opinion. If you want to iterate just over keys or values, go for it. But when you have access to both so easily with some simple syntax, just have access to both, and then if you need the values and you only thought you wanted the keys, hey, you got them both anyway. Okay. Any questions about our data structures? Yes?
So lists in Scala, is there the equivalent of just immutable linked lists?
Yes, so the question, lists in Scala, are they the equivalent of immutable linked lists? Yes. Which we'll talk about in depth later in the semester. Just a quick note on that, the prepend operator is very efficient for those lists. If you want to append to a list, using prepend is much more efficient. But again, as I mentioned on day 1, we're not too concerned with the efficiency in this class, so we'll get away with it. But if you do want to start being concerned, prepend is a very efficient operator for that. Append is not. Append is very expensive. Any other questions on data structures? Yes.
For an array, if you have an array with like a size of 10, put 12 variables into it, how does it handle lots of variables?
It will. So the question is, if you have an array of size 10 and you want to add 12 variables to it, how does it handle that? You're going to get an error. You're going to get an index out of bounds. So when you say array at index 10 store this value, your size 10 is only going to have indices 0 to 9. Once you say array of 10, you're going to get the error, index out of bounds, and your program crashes. So you won't be able to get those 11th and 12th elements in there. You have a question?
Can we have lists as keys in the map?
We have lists as, so the question is, can we have lists as keys in the map? Yes. You probably don't want to, but yes, you can.
Even though the list can be expanded?
In what?
Even though the list can be expanded?
So lists are immutable.
Yeah, but they can still be expanded.
No, because it creates a brand new list. That's where one of the subtleties of the immutability comes in. That list can't change as the key, but you can take that list, append an element to the end of it, which creates a brand new list without modifying the original one, and then we can work with that new list. So that key doesn't change. So it doesn't mess up our hashing in the hash map. You have a key value pair, key that's a string, and a value that's a Boolean. Absolutely you can. And you can nest types as much as you want. So if you want a list of arrays of maps of arrays of ints to Booleans, you can do that. You can nest these things all you want. Usually we want to avoid that, and we do that by creating objects, which we'll start talking about on Friday. Just because that thing that I just spit out, that type is just a mess to read. It's tough to follow your code, but you can certainly do that. Any other questions about data structures? Can you change the values of a map once they're created? Yeah, you would add a new key value pair with the same key, and it'll overwrite the value at that key. It'll just replace it with the new key value pair. You can't have duplicate keys just like in Python and JavaScript. So if you add that new key value pair with the same key, it'll overwrite your first element with that key. That first value with that key that you added won't be in the map anymore, in the new map that's created. All right.
Is there like a middle ground between an array and a list? Like, because like list is inefficient, but you can like add stuff onto an array. So is there like some sort of list that like stays together in the around basically? You can expand on it and it stays together. So it's
This is a great question. The quick answer is not quite. So the question is, array it has a lot of optimal features but can't be expanded. A list can be expanded but loses some efficiency with that. Is there something in between that gets the best of both worlds? Not quite. I mean, kinda. And this is something you're going to dive very, very deep into in 250. 250, you're going to talk about all kinds of data structures and all the trade-offs between them. And when I say a list has inefficiencies, it's really just trade-offs. There's trade-offs between an array and a list. And one of the big things as a developer is choosing for your specific application, for your situation that you're going to be using that data structure for, what's the most optimal for your situation. So there are cases where you just never need the ith element of a data structure. That's a good place to use a list, typically. If you're only accessing the first few elements or something like that, a list is going to be most efficient for you. If you know you have a fixed number of elements, an array is going to be efficient. It's just all about what situation, what data structure each situation calls for. It's a little outside the scope of 116. We'll just throw a few data structures out there and say, hey, aren't these neat? In 250, you're going to really weigh those trade-offs and decide which one is best for your situations. I guess the shorter answer to your question, a hash map is kind of a blend between the two. It gives us the best of both worlds, but a hash map doesn't give us any sorting. There's no ability to sort at all. So if you ever need the elements in sorted order, a hash map won't suffice. So there's always going to be some trade-off. Okay, so today marks the beginning of our first learning objective, program execution. So for these 2 weeks, these 6 lectures, we're going to focus on these 3 bullet points. By the end of these few weeks, we want every one of you to be able to do these 3 things. Write and run automated tests that verify the functionality of a method. This is what we're starting today and continuing on Wednesday. Implement and execute and trace through the execution of programs that pass references of objects to methods. So we're going to learn what's a class, what's an object, and what does it mean to pass something by reference. And you should be able to write programs that do that. If I have a lecture question that says, write a method that takes an object as a parameter, et cetera, you should be able to write that. And also if I give you some code that has a method that passes an object by reference and modifies the state of that object, you should be able to trace through that code and see exactly what happens. And finally, marking the stack and heap, what we'll get to next week, looking through the execution of a program and tracing how memory is stored. When I create a variable, where does that variable go? How is it stored in memory? We're going to talk about things like stack frame, the difference between stack and heap memory, and I'm really going to hit you with the references to go along with these second 2 bullet points are kind of in conjunction. References mean that we have a reference to a memory address of an object stored on the heap. We're going to talk all about how that memory works. For today, let's talk about automated testing. Oh, one more thing. I feel like scrolling. Intro to Scala done. And the first homework is out. There are a few little details I still want to add to these documents, and we'll get a little bit cleaned up. But you can check out what the first few homeworks are, what the descriptions are, what you're being asked to do for these homework assignments. So just a reminder, it was a week ago since we went over the structure, so just briefly I want to talk about the structure of the homework. There will be at least one homework assignment for each learning objective as the application objective for that section, for that portion of the course, for that learning objective, you only have to do one of them to get the application objective. So you have your choice between building a physics engine or writing a rhyming dictionary. So these are your choices for the first one. You only have to do one. Of course, you're highly encouraged to look through both of them, read through them, and then whatever application interests you the most, or what most of you probably do, decide which one you think is easier, but I guess that can't stop you from that. But choose one of these, and then do that for your homework. And next week's lab is going to be the homework introduction, where the TAs will help you get started on the assignment, get things spun up. But there's nothing stopping you from looking at it early. I highly encourage you to at least read these documents before lab. If not, actually getting started, writing the code, submitting to AutoLab, and starting to play around with the assignment itself. This week's lab, yes, there is lab this week. It's kind of a welcome lab. The objective for today's lab is to take this GitHub repo where I have all the examples from class and getting this repo set up on your laptop in your IntelliJ so you can run the examples and making sure your versions of Scala, the JDK, and everything will sync up well for this course. So just getting your whole environment completely finalized and making sure we won't have to have IntelliJ issues at all throughout the rest of the semester. You can just focus on writing your code and learning the concepts of the course. So with all that, it was more than I thought I had. With all that, let's talk about some unit testing. So lecture question for today is to write your first unit test. We're going to take the lecture question from last Wednesday, and we're going to write some testing for that. We're going to write a test suite to test that functionality. So what's a unit test? What's testing? What is all this stuff? So let's talk about this. How do you know if your code is correct? This is a big fundamental question in software engineering. You write some code. How do you know it's right? Well, you can submit to AutoLab, but that's only going to exist during college, and some courses won't have AutoLab. You're not always going to have that crutch. So we have to wean you off of that at some point, and this is where some of that starts. So this isn't going to always exist. So, but this is kind of the first step of testing. So there's kind of like phases in your evolution of testing your code. First, in 1.15, you have UB infinite. You bang out some code, it looks right, you click submit, and you get your response. Or you have AutoLab assignments, you submit to AutoLab, and then you rely on professors to write these grading scripts to tell you if your code is right or not. That's like step one. We got to start you somewhere, so that's where it starts. The next one, we finally, somewhere through 1.15, hopefully we can get you to finally write main methods and call your methods. Actually, you didn't need main methods in Python or JavaScript, but just to call your methods, print the values out to the screen. This is what we did in last week's lectures. Just call the methods, print the return values to the screen, and see if things look right. Like, hopefully you're at least at that point right now. In Scala, you should be able to write a main method, call your method, and print the value to the screen and just see if it looks good. If it looks good, you're feeling good, you submit to AutoLab, and then you see if you get your points or not. The next step is going to be what we want to talk about today, is unit testing. How do we automate these tests a little more? I even looked at this slides, I did have. So first, right now, print to the screen, sure. But what happens when you have very large projects and lots of files? Say you have this huge project, hundreds of thousands of lines of code, thousands of methods, hundreds of files, just a massive, huge project. And you make one change in a function that's called hundreds of times throughout this entire code base. How do you know that that change didn't have some ripple effect that broke something way over here? You're not going to have a main method that prints out thousands and thousands of lines of output and manually verify every single one. At some point, using a main method and printing to the screen is not going to suffice. We're just not going to get away with that for very long. So how do we do this? We're going to start writing what's called unit tests that are going to automate this process. It's going to effectively get a value, check if that value is what we expect, and if it's not, It's going to flag us down and say, hey, developer, we got a problem over here. And then you can go fix that problem. So you have unit tests throughout this entire code base. You make that one change that everything depends on. You run all your unit tests for all of your files in your entire code base. And if anything broke, it's going to flag you down and say, hey, this unit test over here failed. You better look at this and see what happened. That change you made broke something. So for unit testing, our goal is to get all of our tests to pass. If even one test fails, the entire code base fails. This is an all or nothing thing, one failure, and it's going to say, hey, your code's broken. We don't want to release buggy code. Doesn't matter if there's just one bug for one specific case. We want to fix that. We don't want that going out to production. We don't want our users, our customers seeing that bug. So unit testing is built for one test. Fails the entire code base. So let's say this in Scala. And there are a few new things here. I'll go over them. Where are we? Are we frozen on Twitch? Is it just mine? Oh, Scala unit test. Okay. It was still in my repo, like 10 minutes ago or so. Anyway, so here's our first unit test. We'll go through all the pieces of this. But this is how we're going to automate our tests. So first, we have a new, I'll save that for later. I don't want to talk about that yet. But we have a new library that we're going to import. This is not part of Scala. We'll talk about that in a little bit of how we're going to get this library. We have to download this library. It's not going to come with IntelliJ. It's not going to come with Scala. We have to download this somehow. But in our code, we're going to import it. And if it's already downloaded, we will have this library called Scala test in our project, and we'll be able to use its classes, objects, and methods. We're going to create a class. For now, this is kind of like the main method. Just take this for granted and type this line. But as we get further, we will understand exactly what this is saying. But create a class with whatever name you want. If I say create a test suite named whatever, that's where that name is going to go. And then extends fun suite. Fun is short for function. This isn't going to be all that fun, depending on your outlook. But a function suite to be able to test the functionality of some of our code. Now we use this syntax. We're going to write test, and in parentheses, some name for our test, whatever we want to name it. And then in the body of this test, we're going to do all our actual testing. And here, this is any regular body of code. We can put any variables, create whatever we want in here. But this body is going to be executed when this test is executed. And the big thing here is these assert calls. So we can do whatever we need to do for testing, and then we're going to have calls to the assert method, which is part of this Scala test. This underscore is our wildcard. It means import everything in this package. Part of that package is the assert method, and we're going to call this method to be able to test our code. If assert is going to take a Boolean expression and then optionally some other value, a string, but it'll be auto-converted. It'll call toString for us. Here we're giving it doubles. This Boolean value, if this is true, the test passes. If it's false, the test fails. So we want to give it some Boolean check. What are we checking for? Well, I want to know if compute size of this large value actually returns large. If that returns large, my method had the right functionality. So I'm happy about that. So that's going to be my Boolean expression. If that fails, I just want to give myself the string. The string is what's going to be printed to the screen if the test fails. I just wanted to say, hey, your large double, this 70, you failed on 70. Look into that. You got some work to do for debugging. And then the same for the other values. I'm going to check 50, 10. Those should return medium and small. And if all three of these values return what they're supposed to, then this test suite is going to pass. I passed all my asserts, so it's going to pass. And I'm going to get what's called a green bar, which is a beautiful thing to see. You're going to get a big green bar in your in IntelliJ. It's going to say, this test passed. Good job. So, is this enough testing? It's going to be a huge question really throughout your careers. When do you stop testing? What is enough testing? Yeah.
For the fail message, does that just like display in console automatically?
The display message displays in console only when the test fails. So if a test fails, it'll say test failed, and then it'll give your output, whatever you gave it as that second parameter. And a second parameter is optional, highly recommended, but you can just give these a Boolean, and then you just get test failed. You better guess why. Actually, Scala test is pretty good about giving you some feedback, but it's always helpful to have more. So is this enough testing? And we'll talk about this throughout this semester. For a lot of, this slide's probably good time as any to talk about this. For today's lecture question and for any homework, your homeworks will be 3 numbered objectives and a primary objective. For the numbered objectives, you'll have to submit test suites for it. And and the question AutoGrader is really going to ask is going to say, is this enough testing? When is it enough? So I'm going to check your test by having incorrect solutions in the AutoGrader and run your test against all the incorrect solutions. Your tests have to fail all those incorrect solutions, pass on my correct solution, and pass on your own solution. And you'll get that feedback of how what passed and failed in AutoLab. Even then, these won't be comprehensive. That won't be where your testing ends, but you can at least get started with the AutoLab output to kind of know you're on the right track of building the right functionality. It doesn't necessarily mean it's exact functionality. We'll talk at length about that throughout the whole semester. But when is it enough testing? So first, is this enough testing? Are we confident that the compute size method is implemented correctly if it passes this test suite? Assuming that the cutoffs, I think they were 60 and 30. I believe. Yeah, 60 and 30. So here's the correct solution. So assuming that anything over 60, we want that to be large. Anything between 30 and 60, including 60, excluding 60, but including 30 is going to be medium. Then anything less than 30 is going to be small. So assuming that's the exact functionality that we want, is that test suite on the previous slide enough to make sure that we are correct? No, absolutely not. So no, and here's an incorrect solution that passes the test. If I accidentally coded my boundaries at 65 and 20, I'm still passing those tests because I was only checking 70, 50, and 20. My short-term memory is failing me right now. But we're only testing 3 data points, and we're not testing anything close to those boundaries. So we're not really getting comprehensive testing here. We can have a lot of incorrect solutions that are going to pass that test suite. And you have this a lot. In your homework objectives, you'll write a test suite, and my feedback's going to say, I have an incorrect solution. Your test passed my incorrect solution. What's going on here? And then I'll give you some cryptic name of that incorrect solution, so you have at least some cryptic hint of what to look for. So if I have this as an incorrect solution, and that's your test suite on the previous 2 slides ago, it's going to say, hey, you passed an incorrect solution. You got to do more testing. So let's do more testing. Let's check those boundaries. We'll check right at each boundary and make sure that we get the right output for each one of those. Is this enough testing? This one's a bit more spotty. So if you stop testing here, you're probably going to be fine. It's quite comprehensive. There are obscure solutions that you could throw at this that it's not going to pick out. For example, maybe your method has weird behavior on negative numbers, which wasn't defined by the lecture question and wasn't tested. But what if you did define, okay, negative numbers, the shipping cost should be 0, or No, that's not what I want to say. For negative numbers, technically by the description, it should be small. But what if for negative numbers, they just happen to end up being large? You're not quite testing that, but really, if you have a physical scale that this software is hooked up to, I mean, you're probably not going to get negative numbers on this scale, but maybe, I don't know. But is this enough? Probably, yeah. This is probably enough testing for this specific question. But you could do more. You could expand on this. Here's our first application of data structures. We could give this lots and lots and lots of tests. So if we keep testing the way we did on the previous slide, we're going to have a lot of variables. We're going to have way more than we want. So I'm going to split this into data structures and create lists of all of my values for each large, medium, and small. And I expect every value in the large list to be large. I'm going to iterate over those and expect that to be large. Iterate over the mediums, expect those all to be medium. Iterate over the smalls, expect all those to be smalls. And I'm testing my negatives as well here, just in case I had something weird. Maybe I was taking the absolute value and some of those large negatives turned out to be large packages. I don't know. Realistically, we should just define the behavior of negatives and then test those properly. But we'll assume they're supposed to be small because it's less than 30. And then just one example, appending to a list. If we want to add another one, I just wanted to show that adding to a data structure, I'm reassigning large doubles equals large doubles with this value appended to it. So just a quick reminder on our data structures. Now this is great. This is more testing. More testing is usually better. It can't hurt. But there is always this kind of fuzzy question out there, always out in industry as well. When do you stop testing? How much testing is enough testing? And it's kind of I don't know, each developer should answer for themselves, I guess. When are you confident that your code is right, that it's actually fully correct? It's a big question. It's a tough question. So I talked about this earlier. I jumped ahead because I wanted to say this earlier. But for each homework, you'll get your tests. You'll submit your method and your tests. Your tests will be ran on your method, my correct method, and then several incorrect solutions. And your test should appropriately distinguish between them. Except for the lecture questions, on the homework objectives, I'm not going to test your objectives directly. Your only testing is the tests that you're writing and running against your test. So I have the correct solution and the incorrect solutions to give you some hints, like how well your tests are performing. And if those are looking good, you know you're on the right track for testing. But I'm not directly testing your functionality. It is possible to mark all of my incorrect solutions as incorrect, pass the correct and your own with that test suite, but still have some errors in your code. I'm not going for comprehensive incorrect solutions. I'm not going to write an incorrect solution for every possible thing that can go wrong. I'll hit the big ones, but I'm not going to do every single one. So it is possible that you can still have errors. So you do have to be aware, even if Autolab's saying, hey, you did pretty good on that objective, you still might have errors. It's up to you to look at your tests and make sure they are comprehensive enough for you to be confident that your method is correct. And then for the primary objective, I'll run my tests. If you have an error in objective 1 where you just weren't testing something silly and your method makes that mistake that you weren't testing for, you could really have some frustration on the primary objective. Saw it a lot over the semesters. It can get really frustrating if you have an error that wasn't picked up by one of the incorrect solutions. So we want to be very clear. My incorrect solutions will not be comprehensive. You can get past that objective with errors. It's up to you to test your code. Oh, yeah. I can do this in 5 minutes. But so I mentioned we need that library. We have a library that we have to import, that we have to download and link to our project. We're going to do that with Maven. Those of you, the few of you who've had lab already have gone through this. Lab this week will walk you through it. But I want to get you up and started for the lecture question, obviously because you have to do that before lab. So to do this, we're going to use Maven through a pom.xml file. So if I go to the examples repo, for example, I have this pom.xml file. which is going to have all of the libraries, the external libraries that we're going to use in the semester. So this POM file, if you want to just cut and paste this into each one of your projects, go for it. I don't want to focus too much on POM. It's not really what the course is about. We're just using that for dependency management. Maven can do a lot more than this. We're just going to use it for dependency management though. And this first one, this is the first one that we'll need. The only one you'll need right now is Scala test. If you put this dependency in your POM file, or copy this POM file, or download the one that's linked in the schedule, if you use one of these POM files, put it in the root directory of your project, and then go to this sidebar here, go to Maven, and click this refresh button. That's going to look for a file exactly called pom.xml that's in this exact format, and then it's going to look at each of your dependencies and download those dependencies and link them to your project for you. So if I say I delete this, it might not delete the library for me. Oh yeah, it did. So if I get this error, import org.scalatest._, and I get that error, I can't find Scala test. What the crap's going on? Well, it's because it's not in my POM. So I go to the POM, I add that library, refresh Maven. There's so much stuff. Then all those errors go away. Now I do have that library downloaded, installed. Maven takes care of all of the linking, everything that I need. I just add that to my POM, and it'll download that library for me. And anywhere in this project, I can start using that library. So getting your POM set up with Scala test, it will be the first step to doing the lecture question. Import Scala test, extend fun suite, and then start writing your test suite. How do you test that lecture question from last Wednesday? Any questions on this? See everyone Wednesday.